All right. Casey, what number?
55.
55. Read.
Volume of the depth of the water.
I should remember that.
It's like a tank.
Like, oh yeah, okay. So yeah, what is V of 0? So we have a hemispherical tank. The formula or the function is this. So the D is the depth. So again, reading. So this is the type of thing I'm talking about. As far as the quiz goes, and we'll talk more about this on Monday, but really up through here, section 2. Section 2 is probably the main thing that the quiz is about, because section 1 was just about the functions and kind of the early things about a function, domain, range a little bit. But this section's really about graphs, which is mostly what the functions are going to be like on this first quiz. Even, odd, periodic, that's going to be a big part of it. Along with domain range, reading, so this has a lot of examples of kind of story type problems or descriptions of the graph represents this and what is an answer. So a lot of the questions are going to be that kind of stuff. Now, what we're going to talk about today in section 3 is specific types of functions like trig functions and exponential and log and polynomial functions and what those look like. But you're going to get to use your calculator, so it's not like you're going to have to memorize those. So some of the problems will be like this, where I give you a graph of a function. Others might be I give you a trig function or an exponential function and then ask you questions about it. And so you might want to look at the graph, or you can plug values in and you'll get to use your calculator. So section 3 is really not that different from what is going to be here. Now the homework today on section 3 asks a lot of questions specifically about those types of functions, domain, range, those kind of things, maxes, mins, x-intercepts. But that was all stuff we talked about in section 2. It's just that you'll have to graph those. You'll look at a sine graph or look at a tangent graph or look at an exponential graph and you'll answer those questions about it, or a 4th degree polynomial, right? But you can graph them and that kind of thing. You're not going to have to memorize what these graphs are. Now, with that said, as we go forward, you really do need to know what an x squared graph looks like, a sine graph looks like, because they're going to start popping up in no calculator situations. But for the first quiz, you'll have your calculator. So most of the ideas on the quiz are really represented here in section 2. All right, so anyway, by putting a 0 in there, we're saying what's the volume when the depth is 0? Well, that would be 0. What's the volume when the depth is 10? Well, then it's full, right? And now, I would probably give you a volume formula for something. I don't think they did they? Some of the books, now some of these books have been recovered. So if you've got a book that's been recovered, then you don't have those. But in the front of your book, there are a bunch of formulas, but some of you have them and some don't. And you don't get to use your book on the quiz anyway. So, easy formulas like area of a rectangle, stuff like that. But I would probably give you this. Well, the volume of a sphere is 4/3 pi r cubed.
Yep. Yeah.
So half of a sphere would be 2/3 pi r cubed, right? So this would just be 2/3 pi and then 10 cubed, which is 1,000. So 2,000 pi over 3. 2,000 pi over 3. Okay? And then the other question is, which of those graphs would be the picture of the volume? And what'd you say? C? I would say C. Because in the early, when the depth is like, I'll say 1, you get a certain volume. Then when the depth goes up to 2, in other words, you move over 1 on the x-axis. So if you're picturing graphing this, it's the d-axis actually, right? The input axis. You go over 1, you're going to go up a little bit. You go over another one, you're going to go up more, right? It's going to go up faster because that second inch of depth has more water in it. And the next inch of depth has even more water in it, right? And so it's going to be curved. What's the name? Concave up, right? So you're looking for a graph that's concave up. Now, A is concave up,
But it doesn't start at 0.
but it doesn't start at 0, right? And so you know it can't be B because it's not going to be linear, right? And it can't be D. It's not going to be concave down. It's not going to be growing slower. It's going to be growing faster. Now, if you had something like this you were pouring water into, right? Now that would be a concave down situation, right? Every inch that it goes up, you'd be getting a little less. adding a little less each time, and so it would be curving down, that sort of thing. Okay, so good one. What else? Was that in on that one? Okay. What else? Yes. 56. 56, is that the one with the temperature? Yeah. Okay. The child's temperature has been rising for the last 2 hours, but not as fast since we gave the medicine an hour ago.
Yep.
Is that what it was? Okay. So, and did it say what 0 should be?
Yeah, temperature when the medicine is administered.
Yeah. So if this is time, and then this is temperature up here, right? So time 0 would be the temperature when the medicine was given, right? So that might be like so, right? Now what's happening after that?
It rises quickly.
It's rising less quick.
So it's concave down. Rising at, one of the things we'll say is, some of the terms we use is increasing at a decreasing rate. Would that be a good way to say that? It's increasing, but at a decreasing rate. That's concave down, right? But it says it's still rising. It's been rising for 2 hours, but not as much since we gave it an hour ago. So what's before that then? Concave up. So the point at where we gave the medicine is called? That point on the y-axis is called an y-intercept, but what else? Starts with an I. Inflection point, where the concavity changed. This would be the spot that the temperature was rising the fastest. Now, I'm not sure. Do we know that it was concave up?
No, it said like it was rising.
It said it was rising, but after the medicine not rising as fast. So could a person have drawn maybe this to here and then that?
Yeah, that's how I drew it.
Oh, okay. And I think with the information given, that would be a possibility, right? It doesn't give us enough information to really say that it was increasing at an increasing rate. I don't believe it does, right? So it's rising, it's not rising as fast after the medicine was given. Now, realistically, okay, realistically, chances are it's probably curving, right? I mean, this would tell me that that medicine just acted instantaneously, right? As soon as you took the medicine, boom, it went down. Probably not, right? I mean, it probably was a little more curved there. Now, in the early parts and then later, maybe it is linear, but, you know, who knows? We're going to have a name for that. Well, not a fancy name, a sharp point in a graph. If you have a graph with a sharp change like that, that's going to be of interest to us. Most functions don't have that situation, though. Most functions are gentle curves and gentle changes. And, of course, we're going to be interested in changes. Rate of change, right? It's one of the things we've already talked a lot about. Okay, what else was in that? Was there more to that one?
Yeah.
What's the significance of the fact it was increasing from -1 to 1? Or what's the significance of the fact that the graph is increasing? Well, it means her temperature was rising. I mean, that's what they meant. That was weirdly, strangely worded, I think. What's the significance that the graph's going up? In other words, what's it mean applying to this situation? It means that her temperature is rising. Okay, that's all they wanted there. And then C, what's the significant? See, then they said concave down there, which is interesting to me, but I really don't think they said anything. But concave down means what? But compared to the temperature.
Eventually it's going to come.
It's leveling off, or the fact it's not rising as fast, right? It's not rising as fast. Now we assume, yeah, it's going to come back down probably. But the fact that it's concave down, the significance there is that it's not rising as fast. It's rising, but the rate is decreasing. Okay, what else? 69. Suppose that G is concave down from 0 to 10, and they give you some other points. Okay? All right. So here's the G graph. Give me some of the points they tell me. G of
1 is 4.
1 is 4.
G of 5 is 2.
Okay, so again, getting used to this notation. Really, this is about reading, math, and understanding what it's telling you about the situation is really our emphasis here, because we have to be able to do this as we go into calculus, to be able to work these problems. So what I'm being told here is I have a graph that's got the point 1, 4 on it. So as soon as I see that, I'm going to draw a picture. Okay, and then I've got the point 5, 2 on there. And they tell me that G is concave down the whole time, right? Or at least from 0 to 10, right? From 0 to 10. Okay? Explain why G of 3 is greater than 3. Now, first of all, let's just understand, what are they asking? What does that mean to you? When you hear G of 3, what do you think?
Input 3.
The y, right? When the x is 3, right? But that's the y value, right? What this is saying is the y value at 3.
Yeah.
Okay. So this is saying that the y value at 3 has to be less than 3. So here's, right? Or greater than, excuse me. So why does the y value at 3 have to be above this point, right? That's what it's saying.
Because it's concave down between 0 and 10.
Okay, yes, that's not enough, but you're on the right track.
If it was at 3, then it would just be a line.
Okay, the key is the slope between these 2 points. This is down 2 and over how much? Down 2 over 4, right? Which means it's a slope of 1/2, which means if negative 1/2. So if we go down 1, we would go over 2. That would be, so that point, G of 3 is right on that line. Linear. What's the concavity of a line? There isn't any, right? It is not concave either way. So if a graph is concave down, it's got to curve above this line. I think if this was a quiz question, a picture is almost necessary. I mean, you could write it out in words, but I think it would be hard to describe. I think a picture along with some words here are important. So, since it's concave down, and since you would have to say the point G of 3 equals 3 would be on a line between those 2 points, so therefore, the graph of G has to curve above that point. That's your explanation in part A, okay? Part B, find a number L such that G of 4 is greater than L. So, G of 4 is what?
Where y is.
The y value
Where x is at.
at x is 4, right? The y value at x is 4. Now we know, so wouldn't it be finding that point on the line?
Yeah.
So if this were a line, that would be what? Would it be 1.5? No, 2.5. You're right, because this is, my picture's awful, isn't it? This point is supposed to be at 2. Okay, there's 2. 3, 4, right? This is drawing to scale. Okay, so this point's at 2 and this point's at 3, right? This would be at 2.5, right? So this is at a y value of 2.5 right there. G of 4. So find a number L. So we know what? We know G of 4 has to be greater than 2.5, right?
Yeah.
It's got to be above it. So would that be an acceptable answer for L? Find a number L such that G of 4 is greater than L. Isn't that it?
Yeah.
That's it, right? That's it. Would other answers work?
Well, because we don't have an exact graph that we're looking at, so there could be a different one.
Right, so give me one. I mean, give me another number that would be acceptable for L. Give me another number that G of 4, the y value at 4, is greater than.
2.6.
I think you're going the wrong way. Because 2.6 would be here. Do we know G of 4 is above 2.6? we know it's above 2.5 because it has to be above the line. So G of 4's got to be above 2. It's got to be above 1. Right? It's got to be above, it's got to be above negative 1,000. There's an infinite number of answers you could have that would be acceptable here. Right? Now, I don't think anybody would do that, right? I think you would probably mostly put 2.5, but think about what it says. Find a number L, so, and this is just mathematical language, right? So they're trying to run a lot of this at you to get you to interpret it. Find a number L such that G of 4 is greater than L. Well, what we know is since this graph curves up over the line here, G of 4 has to be greater than 2.5, which means it has to be greater than any number less than 2.5 as well. Okay? All right. So, interesting question. What else? 60.
Yes.
Oh, yeah, old completing the square stuff. Okay? Now, so they say f of x is this, and what's g of x?
X squared.
Plus 4x
Plus 3. We're going to do a little look at this when we're looking at polynomials here in a little while. But this is related to work we did yesterday when we were doing the shifting stuff. Okay? Because what I want you to be able to do is when you look at these, know that they're both parabolas, obviously. Okay? This one's an easy one to graph. I mean this, oh mercy. Okay? Y equals x squared, right at the origin, that kind of stuff. This is a parabola that's somewhere else, right? Now, if we could do some work to this, hint, hint, complete the square, if we could write this another way, it would be easier to know what the graph of this is like. And so here's what completing the square is. See if we can remember this. What we do is we're looking for a third number there that will make a perfect square, right? Like x squared plus 10x plus 25 is x plus 5 squared. Remember that?
Yeah.
Well, the way you do that is you take half of this number and square it, right? So half of 4 is 2, squared is, so if there had been a 4 here, we'd have had a perfect square. But we can't just add a 4 here because now this number's different.
Yeah.
So let's take away 4 at the same time. So let's add a 4 and take away a 4. So what I'm going to do is I'm going to write this now as those 3, which would be x plus 2 squared, and then 3 minus 4 is minus 1. Okay? So if I was to now work this the other way, if I was to FOIL this out, I have x squared plus 4x plus 4 minus 1. 4 minus 1 is 3. So this is the same as that. This is the same as that. But now look at what an advantage it is to look at this. Because this is just a square, a parabola shifted where? Left 2, down 1. So if this function would have been written this way instead of this way, I would have known right off the bat that this is left 2, down 1, and this is this parabola right here. And another thing I know about parabolas is the normal parabola that hasn't been stretched or shrunk goes through 0, 0. It also goes through 1, 1. It also goes through 2, 4, right? So I know a normal parabola from its vertex goes over 1, up 1, and then goes another 1 up, and then like 3 up, right? Because it's got to go over 2, up 4, right? I mean, that's, unless it's been stretched or shrunk. So I would know a really good graph of this without a calculator, see? So the ability to do this is nice if it makes you that. Now, I will tell you, probably not going to have to do that very often. I could see you getting in a college class, though, where your college professor made you do a bunch of this. Because they really like making you do stuff by hand. Okay? I don't know why, but, well, I do, but it just seems like they get in there and they want you to do a lot more algebra maybe than we sometimes do here. So we'll review it, we'll do some of it, but I'm not going to quiz you on it and beat you over the head with it a whole lot. But that's what they were getting at there. Okay, show that it's a shift left of 2 and a down 1. All right, what else? What else? Okay. We'll have some work time here, later, and if you do have some other questions, again, the answer book's there. Come see me individually. Really, if there are some, let me know. All right, go ahead and get your notes out, and we're going to run through this. I'm going to have, we're going to do a couple different things here. Let's see what's happening with our calculators. Why did it do that? Joe, were you able to get on intervention? Yeah, it must have been the calculator. Okay, let's. I hit pause, but then I hit record. All right, so try logging in again. Try logging in again on your calculators. Try logging in again. So we got 1, 2, 3, 4, 5. Okay, so we should have 25. So Nicole, you're still not. Andy, yours isn't? And Blair, yours still isn't? I got 22 of them, looks like, so must be just all right. All right. Here's what we're going to do. So we'll kind of try to follow the path, I guess, of the book here. I'm going to kind of go off track of it a little bit. So first one is polynomials. So if you look at polynomial functions, all right, and I'm going to actually, I think I'll probably have you, or we'll do a little something on that IXL again here, maybe just together. We'll kind of see how that goes. I tried it this morning. It looked pretty good. So polynomial functions are the types of functions that are like ax to the fifth plus bx to the fourth plus cx to the third, dot, 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 kind of thing. Okay, in other words, nice whole number powers, 5s and 4s, no fraction. I mean, the a's and b's could be fractions, but no fraction powers, no dividing, no x's on the bottom, no negative powers. Those are polynomials. You've worked with them forever. Algebra 1, Algebra 2, right? Quadratics, cubics, linear, those are the most common that we look at. When you have an odd power, okay, an odd power, so like x to the first or x to the third, I'm talking about the highest power now, x to the fifth, right? You have a situation where the tails go opposite directions. So x to the fifth, now they don't always look like this, but the tails always go opposite directions, right? And what happens if you have a negative out in front of the leading coefficient? Flips around the x, because what happens, that's like a negative on the outside, and then when it's on the leading coefficient, it flips vertically, and so what happens is the tails go opposite. So normally the tails go from down on the left to up on the right, but if you have a negative leading coefficient, it flips the other way. The range of those is always all reals, and the domain is always all reals. You can always put anything in. They're continuous, no breaks. So we're dealing with polynomial functions. A lot of nice things happen. Domain is all reals, range is all reals, that kind of stuff. You could get a lot of local max and mins. Remember, so thinking about the terminology back in section 2 now. You could get a lot of max and mins. You can have inflection points, a lot of concavity changes potentially in those kind of graphs. Okay, that kind of stuff. All right, so they're really interesting ones to look at in calculus situations because they have a lot of those things. Okay, and of course your even powers, your x squared, your x to the fourth, your x to the sixth. Oh, and then I might mention the number of humps. The number of local maximums depends on the power. So like an x cubed, the most it can have is the 2 humps there, right? One of the things you probably remember from Algebra 2 is if you have an x cubed, at most it can have 3 solutions. Now when we talk about solutions, we're talking about setting it equal to 0. Well, for us, that'll mean where it crosses the x-axis. So if you think about a cubic, if I put an xy axis in here, right, something like that, well, the most it could cross would be 3 times. It could never cross more than that. Now, it might only cross once. It might only have 2 solutions or 1 solution. But it would always have to have at least 1 solution. A cubic would have to cross the x-axis sometime, right? Sometime. So you get that kind of thing. So a 5th degree could look like this. Could have as many as 4 humps, if you will, right? It could cross as many as 5 times, solution-wise. Okay, x squareds, of course, look like that. And x to the 4th could look like kind of a W shape. And x to the 6th could have, whoops, that's not a V. It's always going to be smooth. There's not going to be any V. There's not going to be any sharp points. A polynomial is always nice and smoothly curved all the time. And so an x squared is always going to be a parabola. X to the 4th can sometimes look like a parabola. It might just have the 1 hump, but it often will have 3, like so. But the tails always go the same direction. And of course, if there's a negative in front, flips it about the x-axis, then the tails will be going down. And so again, all reals for the domain. Now the range, though, is different, right? The range would be from the vertex, for example, wherever that is, on up. That would be the outputs, right? There'd be no outputs down below. So if you were solving, you know, you've done this. If you're solving an quadratic equation, here's a quadratic equation right here that would have no solution, right? Is there any number you could plug into there? 3 squared is 9. Negative 3 doesn't work because that's also 9, right? You would solve that. You would subtract 9 for both sides. When does x squared equal negative 9? Never. So there's no solution to this. Well, this would be a parabola shifted where?
Left 9.
Yeah, up, because it's on the outside of the squared, isn't it? Yeah, no parentheses. So this would be up 9. Well, it never crosses the x-axis. So x squared plus 9 is never 0. So in a no calculator situation, you'd want to be able to know that. You'd want to be able to look at that and say, oh, there's no solution to that equation, right? It's a parabola shifted up 9. That'd be one way to think about it, is graphically. It's a parabola shifted up 9. That'll never equal 0. So there'd be no solution. So sometimes there's no solution. Okay, so that's just a lot of domain range. These could be even functions, but they might not be, right? And odd could have origin symmetry. They could be odd functions, but they might not be. You know, that just reminded me, I hate to do this, but in the homework, nobody asked about that section on the periodic. Did I do such a great job of teaching that? Like did you do number 23? Is that in the homework?
Yes.
Yes, it was, and I didn't actually get that.
I got that.
Okay. So I did a great job of teaching it, is what you're saying?
Yeah.
Well, thank you. But I don't believe you. So T has a period of 7. Okay? So I was talking about even odd, and we didn't really have a question on those. So T of 0 is 3. So T of 7 is, to back up a little bit, T of 7 is 3, because you go from 0 to 7 on the x. That's 1 period, so it's got to repeat the outputs. T of negative 14, also 3, because that would go left 2 periods from 0 to get an input of negative 14. But then this is the one, why is this a true statement?
Because they're 70 apart.
70 apart,
Divisible by 7.
which is divisible by 7, that's 10 periods. So those inputs, negative 30 and 40, are 70 apart, 10 periods. Do we know what the output is?
No.
No, we don't know that it's 3. We don't know what the output is. We just know they have to be the same, right? Because it has to repeat the outputs every 7 inputs. Okay? So that would be your explanation, since they're 70 apart. And was that it on that one?
Yeah.
Okay. All right. So that's just the kind of thing we had done with periodic. Okay. So anyway, back to the polynomials. So So you don't, I mean, you should know all this stuff. It's really going to make life easier, even though when you have your calculator. If I give you a 5th degree polynomial and tell you to graph it and ask you some questions about it, if you don't set the right window, right? If you look at, remember that cubic we had the other day and our window was only looking at that piece of it? And it kind of looked like a parabola. Well, it wasn't a parabola, right? And you needed to know that from the equation. It was a cubic. So when you're zooming in and out, and remember on the quiz, I'm not going to help you with your calculator from that standpoint. Set a window so you can see it. You've got to be able to do that yourself. So even if you're using your calculator, you may need to know these properties of this function so you can find an appropriate window and know what you're looking at. Okay, so that's why it's important even if you're using your calculator. Okay, all right. Well, I went into the IXL. We're not going to do a whole bunch of them, but one of the things I have starred here is match polynomials and the graphs. So I thought I would look at a few of these here. It starts out really pretty simple. Here's an x squared and a negative x squared, right? So that one's negative, that one's positive. Okay, that's easy. I don't know if it's brilliant. Negative x cubed is which one? That one, right? And that's the positive, just because of the way the tails are going. So again, when you go through this, it gives you a nice, you start getting used to seeing these different ones. Here's an x to the 4th and a negative x to the 4th, right?
Yep.
And again, notice how they look parabola-ish, but they're not. You can see this one's much flatter there down at the bottom. Here's an x cubed and an x squared. That should really be easy to see. Here's a negative x cubed with an x squared. Okay, that's easy. Here's an x to the 4th and an x cubed negative. Okay, there's some here I want to get to. Okay, and then they give us 4 of them. Let's see, here's an x to the 4th and a negative. This would be the negative x to the 4th. This would be x to the 4th.
Bottom left.
Negative x cubed, right? The tail goes up to down. And then positive x cubed, okay, pretty easy. And again, you can sure go through these yourself depending on what you think you need here. But again, a negative x cubed is that one. Positive x cubed, positive x squared, negative x squared. I do have something I want to get to here. There's a reason I'm doing these, so they probably seem really easy. But let's see, would this be an x cubed? This would be a negative x cubed, negative x squared, positive x squared. Okay. Okay, here's what I wanted to show you. Now, they give you some, now they make it a little, well, it's still pretty easy, because it's a negative x to the 4th, it's a positive x to the 4th. So you can really, when they're positive, negative, but later on they get in somewhere, they give you 2 that are both positive x to the 4th, right? So now how would you tell the difference there? Give me a thought. They give you 2 that are positive x to the 4th.
By where like the coordinates of
By what?
Transformation.
yeah, the coordinates of like the vertices.
Yeah, the thing I did when I started doing it, I didn't even realize when I was just running through them this morning real quick. And I didn't realize they had them written up at the top, and so I was just plotting some points. I put a 0 in, and then I would check a couple points, which would be a good thing to do. But I noticed what they did up here is they rewrote them in another version, and you will notice actually in calculus a lot, like that completing the square thing. I said you're probably not going to have to do very much. On the no calculator stuff, a lot of times they will give you functions written in this form, right? Well, why is that good? Well, that tells you some really good information. Like this one tells you what? The cubic is what? Shifted left 3, and the negative on the outside is a vertical flip. So you're looking for a basic cubic, which would be this one, shifted left 3 and flipped. So by having it written in that form, that makes it really nice. Now, I forgot which one that was. Okay, that's this one. So that's down there. But here's another thing. So now when you get one that looks like this, now that's not a shift, right? That's got multiple things written. It's all factored out. This is a 4th degree. Now we know which one it is, but tell me what advantage there is to this writing?
Find the roots.
The roots. Exactly. The roots, remember, are where a function equals 0. So if I set this equal to 0, where are the roots? 0, -2, -1. Because you would set each of those factors equal to 0. So now you're looking for an x to the 4th, and you know that because here's an x squared, here's an x, here's an x. When you multiply that all out, you have an x to the 4th is the highest. So you know it's an x to the 4th, and you know it's got roots at 0, -1, and -2, which is right there. That's where it crosses. So we can go in there, and that was which one? This one? Of course, again, we know it's that because it's the only 4th degree here where the tails go up. So we knew it was that anyway. But later on, they get into some where they'll give you like 4 different x to the 4th, and you kind of have to find them. So it's a nice way to review that idea of when it's written this way, it tells you where the roots are, where it crosses. And that's a cool thing too with polynomials, something we want to know. Okay, so that is about all I have for polynomials. So let's move on. It talks about rational functions a little bit. Rational, the word ratio is in there. Rational means fraction. So we're going to get into these more later on, but an equation like this, okay, something like that is a rational function where you have a polynomial over another polynomial. Okay? The thing to know about rational functions is this is when you get into asymptotes. Now, there's not going to be much of an emphasis on these on our quiz next week. Okay? Not much of an emphasis at all on this. We're going to get into that later on. So I'm not going to say a whole lot about it. Other than to say, at this point, vertical asymptotes is basically when the bottom is 0. Now, specifically, when the bottom is like 7 over 0 or -2 over 0 or something like that. So in other words, in this case, your vertical asymptote would be at x equals 4, because when you put a 4 in there, you get 19 over 0. We know that's undefined. And what's going to happen here is you're going to have a vertical asymptote, and then you're going to have this graph. I don't know what it looks like exactly, but you're going to have something like this, right? Something like this, you know, whatever. Some sort of an asymptote with some weird stuff going on. Okay? And the horizontal asymptote, we won't even get into with one like this. We'll get to those later on. But okay, one of the things on your homework they're going to ask you about is if you had a rational function, they're just going to say, okay, if you had a vertical asymptote at 4, for example. Okay? This is the only thing your homework's going to talk to you about asymptotes, I think. If I had a graph that had a vertical asymptote at 4, like that one, and I shifted it left 3, because we've been talking about shifts and stuff. What happens at vertical asymptote? So where's it going to be now? What I said left, didn't I?
Yeah.
Shift it left 3. It's now at x equals 1, right? What if we shrunk it by a factor of 2 horizontal? Where's the vertical asymptote? At 2. All those values that were near 4 on that asymptote are now near 2 because they're half as much, right? What if we shifted it vertically up 6? It would stay the same. The asymptote wouldn't change, right? And then the same thing with a horizontal asymptote. If you have a horizontal asymptote and you shift, where would the horizontal asymptote be? So there's some questions like that. Okay, nothing too great there. So won't be much about rational functions you have to worry about for the next quiz. Okay, the next thing they talk about, if we keep turning the page here, is okay, exponentials and logs. Okay, we've already been doing some work on exponentials. Now we remember an exponential has to be a number raised to a x. It's a number raised to an x. That's what makes it an exponential. The polynomials had an x raised to a number. Okay. Exponentials, basically what I want you to make sure you understand about exponentials, they look like this. They cross at, the basic exponential crosses at 0, 1. So it's got domain of all reals. You plug anything in. Range is just positives, right? You're only going to get positives out. And then contrast that with your log functions. Now remember, they're inverses here. So this one is going to cross at 1, 0. Remember inverses, you interchange the x and y. Remember that thought? On inverses, we're going to talk about inverses more later too. But just so it's easy to remember here. And then we were talking about log yesterday about domain. You cannot put a negative into a log function. But if you remember what its graph looks like, I mean, I think you should start today memorizing that graph, natural log graph. It comes up over and over this year. Sine, cosine, I think you already got. Parabolas you got. E to the x, I think you probably already got. I mean, this is the one you probably don't know instinctively. Memorize that thing. It's got a vertical asymptote right there at the y-axis, and it just goes. It levels off really flat, but it does keep rising forever and ever. Okay, just like an exponential goes up really fast and really steeply, but it does keep moving out to the right. But it just goes up way more than it goes out. And then this is kind of the reverse of that. Okay? So, not much else to say about exponentials logs. There's not much interesting on these graphs. No local max, no local min, always increasing. You know what I mean? There's no inflection points, always concave up. That one's always concave down. You know, not a lot of changing things happening with those. So, kind of uninteresting from that standpoint. All right, and then what's the last thing? I think it's the trig stuff. And again, you're going to have your calculator, so it's not going to be critical that you know sine of pi 6 is 1/2, right? But it is down the road, right? And there's not going to come a date where we're going to say, okay, let's memorize them. I mean, you should be working on that now. And so I'm going to again show you on the IXL some things you can be doing here. So the trig functions. Well, what can we say about the trig functions? Let's start here with the unit circle. Now, if you've got an old unit circle from class, how many people have a copy of the unit circle from class last year? Okay. Well, I've got one, I think somewhere here that I'll put on our website. On today's homework, I'll just put a link to it, a PDF, whatever, just if you want to have something you can look at and try to memorize those values if you haven't already. Okay, so let's go to pi 6. Okay, so those values right there. Now, again, a couple of just some quick things to remember. SOHCAHTOA, right? What's that mean in SOHCAHTOA? Okay, opposite over hypotenuse. So in the unit circle, the hypotenuse is always 1. Right? So when we talk about x and y, so cosine of, if this is our theta here, cosine of theta is x over 1, which means it's x. So the x coordinate is cosine. That's why we use the unit circle, because the hypotenuse is 1. It makes it nice. And what's sine? Y over 1. So the y coordinate is the sine. Y is the sine. They rhyme, right? Y and sine. Y and sine. So cosine and sine. And so if you remember cosine is x and sine is y, then the quadrants are easy to remember. Cosine and sine are both positive here. Over here, x is negative, but y is positive, right? So cosine is negative over here, sine is positive over here. Down here, both coordinates are negative. So cosine and sine are both negative. I know there's the whole thing with cast and those things, right? You can memorize it that way too. But if you just know the cosine is the x and sine is the y, then you've got it, right? And then of course tangent is sine over cosine, right? Y over x. Opposite over adjacent. So it's sine, this number divided by this number. Okay. But if you know sine and cosine, you're most of the way there. Okay, so 30 degrees, the first one, pi 6, so sine is 1/2, cosine's root 3 over 2. Get to 45, they're both root 2 over 2. Get to 60, pi thirds, they switch. Okay? The x is getting smaller, the y is getting bigger. Right? So therefore the y square root of 3 over 2 is bigger. It's like 0.86 something. Okay, there it is right there, 0.86, 0.5. Okay, we get to 90. Of course, the y value is 1, so that's sine. Cosine of 90, cosine of pi halves is 0 because of that. Okay, keep going. There's 2 pi thirds. And again, notice the reference angle down here. That's 60. That's pi thirds. So you got right here is 3 pi thirds, right? Pi is 3 pi thirds, but you're pi thirds short of that. So that's 2 pi thirds. And so forth. And you have the trig values around the circle. Okay, cosine of pi is -1 because cosine's the x. Sine is a 0. And then it's the same thing all the way around. Okay? So, on the graphs of the trig functions, and you probably saw this last year, but if we look at the unit circle, and let's just do sine, first of all, okay? All right, so theta is the red, right? That's the angle. So we're talking sine of 30, sine of 60, although we should be thinking radians, right? So that's the red, that's this. So this red, I'm graphing along the x, and this is the sine. Remember, sine is the y. So that's what's being graphed here. Okay? So as you go around the unit circle, right, hits its peak, sine is 1 there at pi halves. Then sine, the y value is back down to 0. The blue is back down to 0 there. Okay? And then keep going. Now sine gets down to -1. And then sine gets back to 0. And there's a sine graph. And that's one period, one time around. And then you keep going around and around and around and you get another period. Okay? Cosine is the x. So now we're looking at the green. Oops. Now we're looking at the green part. Okay, so cosine, the x, starts at 1, but as this goes along, the x actually goes down. Oops, I have to show it. Okay, so cosine actually goes down to there. And now the x is getting bigger, negative, then the x is getting smaller, negative, and then the x is getting bigger again, back up to 1. Okay, so it's a neat way to see the connection between the unit circle values, and then if you graph them on an xy, not an xy, this would be a theta, and then the function value up here, right? Theta would be on your x-axis. Okay, and then of course the tangent graphs are a little harder to see, but basically your tangent graphs. Tangent is the slope. I mean, think about it. Think about it in this triangle. Tangent is opposite over adjacent, right? Tangent is opposite over adjacent. Well, isn't that rise over run? It's really the slope of the hypotenuse. That's what tangent is. Tangent is slope. It's rise over run. It's the slope of the hypotenuse in there. That's why here, whoops, that's why at pi halves it is undefined, because what's the slope of the hypotenuse right there at pi halves? Darn it. Let me drag it.
You need to just show it.
Dang, why does that keep hiding? Okay, what's the slope of this line right here? There isn't one. Vertical line has an undefined slope. So there's an asymptote there. Now you go around here, now it's negative, really big negative, so it's way down here, and now that slope is negative but getting closer to flat, and flat is 0, and that's why the tangent is 0 right there. But that's why tangent does what it does. Also, tangent is sine over cosine. So whenever cosine is 0, it's undefined, which is at pi halves. Okay, so a lot of trig stuff. But for the quiz next week, I might give you a trig function that stands for something, the temperature throughout the year. Wouldn't that be a sine type of thing, right? Summer, it's up here, and then the winter, it's down here, and back to the next summer, it's up here, the next winter, right? Great use of the sine curve, talking about temperature over the course of years. But I might give you something like that, but you could put it into your calculator, set your window, trace, be able to find stuff. So you're not going to have these values memorized right now, but you should be working on it and make sure you can get those. So here's what I'm going to do. I'm going to let you work now at this point. On IXL, the homework's going to be the 1.3 in the book, okay? But I also would suggest to you in IXL, there was this match the polynomials. I don't know after seeing that if you think that's something you need. But in the trig section, some of you did some of those in the trig section. These last ones, reference angles, inverses of trig functions, and solving the trig equations, I think those are really good ones to be looking at. We're actually going to do a worksheet on some trig equations on Monday. Like I said, most of the quiz is Tuesday just because I don't really like Monday quizzes that well. So the quiz is Tuesday. We've really done about everything you need to know for the quiz at this point, okay? So we'll answer some more questions on Monday, and we'll just kind of rehash a little bit and focus in on quiz topics. But we will spend a lot of time Monday working on some trig stuff, kind of for the future. All right? Yes?
Me and a couple of other kids are going to be gone Monday.
I will too.
Okay. Yeah. So, well, that's a good reason. Well, I guess we still could do the quiz. So, I would, you guys should be ready to do the quiz on Tuesday, okay? Because like I said, we really are not going to do anything that's new. And I'll have the video of the specific, when we kind of do a review and we talk about those things, I'll have that on there Monday. Okay, if you get a chance to see that. But it's going to be short and sweet. It's just, right, it's graphs, and it's reading the graphs and being able to type in your calculator, be able to set a window on your calculator, you know, so you can trace, kind of like we've already been doing. And then, you know, a lot of this, again, the homework questions in section 2, really, you know, the stuff about even, odd, periodic, that kind of stuff. Okay? I think the only assignment I have on Monday is just we're going to do a worksheet of solving some trig equations, but I don't think I'm going to pick it up. But I mean, we're going to work on them in class and stuff. Okay? All right. All right. Rest of the time is yours. What, Joe, what are the 6 numbers on the back of that calculator? After all the zeros.